research suggesting a new lithium deposit in northern Nevada may be the largest in the world. It's located next to the Thacker Pass mine, not far from the Nevada-Oregon border.
Lithium is one of the most coveted materials in the world right now. Some call it white gold. It's a critical material used in batteries, and of course demand is skyrocketing as energy companies and car makers move away from fossil fuels.
Deep in the high desert near the Oregon-Nevada border lies a vast geological formation known as the McDermitt Caldera. For decades, this ancient supervolcano has sat largely forgotten by the public, even as scientists kept a quiet but watchful eye on it. However, recent developments have shattered that quiet observation. In just the past few weeks, researchers monitoring geological data from the region have detected unusual and alarming signs. Subtle but unmistakable movements that indicate the ground beneath McDermitt is shifting. The data points to an increase in seismic activity, uplift patterns in the caldera floor, and changes in gas emissions. These are not ordinary fluctuations. They are the kinds of signals that send shivers through the scientific community, especially those familiar with the subtle precursors of volcanic unrest. Before we start, hit the like and subscribe buttons for more exclusive news. The McDermitt Caldera, formed approximately 16.5 million years ago, was born from an explosive volcanic eruption that dwarfed most known in human history. It once unleashed thousands of cubic kilometers of volcanic material, reshaping the region and contributing to a trail of destruction that marked the path of the Yellowstone hotspot. While it hasn't erupted in eons, the underground systems that fueled its fury are not entirely dormant. Geologists have long acknowledged that volcanic fields like McDermitt can remain geothermally active for millions of years after their last major eruption. Recent data suggests that this activity may not be as benign as once assumed. The initial alerts came from satellite-based ground deformation measurements. These precise instruments detect even minute changes in the elevation of the Earth's surface. In McDermitt's case, they began showing a slow but consistent uplift across several key zones within the caldera. At first it seemed innocuous, a few millimeters here, a centimeter there, but then the pattern expanded and intensified. Over the course of just a few weeks, the rate of uplift increased dramatically in a localized area to the north of the caldera's central basin. Such a phenomenon typically occurs when magma accumulates beneath the surface, pushing the ground upward. This rising pressure was soon accompanied by a sharp uptick in microseismic events. These are tiny earthquakes, often imperceptible to humans but closely monitored by seismologists. Normally, the McDermitt region sees only a handful of these tremors per month. In the past fortnight alone, instruments recorded over 600 microquakes, many clustered in tight swarms that suggest fracturing rock deep below. Even more unsettling was the depth of these quakes. Many were shallow, occurring just 2 to 5 kilometers beneath the surface, a known red flag when assessing potential volcanic reactivation. Adding another layer of complexity, gas emissions in the region have started to show subtle but noteworthy changes. Scientists monitoring fumaroles and other geothermal features have reported elevated levels of carbon dioxide and sulfur dioxide, gases typically associated with volcanic systems. Though the emissions remain well below dangerous levels for the time being, their sudden increase could indicate that magma is rising and releasing volatile compounds as it moves. These emissions often precede eruptive activity, sometimes by months, sometimes by years. This combination of uplift, seismic swarms, and elevated gas output forms a trifecta that is deeply concerning to volcanologists. Each of these signs on its own might be explainable through minor shifts in geothermal systems. Together, however, they suggest a system under mounting pressure. The key question now is whether this pressure will dissipate harmlessly or escalate into something more dangerous. That uncertainty is what has scientists on edge. What makes the McDermitt Caldera especially intriguing and troubling is its geological context. It is one of the largest calderas in North America and part of a chain of volcanic features stretching from Nevada all the way to Yellowstone. This volcanic corridor has a long and violent history, shaped by the slow drift of the North American plate over a stationary mantle plume. As the continent slid over this hotspot, successive eruptions carved a line of devastation across the western United States, with McDermitt being one of the earlier expressions of this process. In recent years, interest in McDermitt has largely revolved around its lithium deposits. The caldera is home to some of the richest known lithium clay reserves on Earth, a fact that has brought mining interests and environmental debates to the fore. Yet even as exploration teams drilled for future battery materials, few could have predicted that the ground beneath their feet might stir again. Now, those same drill holes could be conduits for rising gases, their measurements offering unexpected insight into the reawakening of an ancient volcano. The broader implications of volcanic unrest at McDermitt extend beyond the geological. If this caldera were to exhibit more serious signs of activity, the consequences could ripple across the region. Although McDermitt is remote, it lies near major transportation corridors and within reach of several rural communities. An eruption, even a moderate one, could disrupt air traffic, damage infrastructure, and force evacuations. Moreover, ash clouds, if they occurred, could affect areas hundreds of miles downwind, depending on prevailing winds. Historically, ash from eruptions in the western U.S. has reached as far as the Midwest, blanketing farmland and affecting air quality. More immediately, there are concerns about how the shifting Earth could impact ongoing mining operations. Heavy equipment operating in the area must now contend with the possibility of sudden ground deformation or earthquakes. Mining companies are beginning to reassess their risk models, even as scientists push for greater access to monitor the evolving situation. The McDermitt Caldera, once primarily viewed as a treasure chest of minerals, is now being re-evaluated through the lens of geologic hazard. What adds to the unease is the lack of precedent for such activity at McDermitt in recent history. Unlike more active volcanoes with well-documented cycles such as Mount St. Helens or Kilauea, McDermitt offers few recent analogs. Its last major eruption occurred millions of years ago, well before human observation. That leaves scientists reliant on incomplete geological records and modern instruments to piece together what might be unfolding. The uncertainty surrounding such a little understood system only deepens the urgency to understand the current changes. Another complicating factor is the sheer size of the caldera. Spanning nearly 45 kilometers in diameter, McDermitt is not a single crater but a complex of volcanic and geothermal features. Monitoring such a vast area requires extensive resources and coordination. In response to the recent anomalies, several research institutions have deployed additional seismic sensors and remote monitoring equipment throughout the region. Drones equipped with gas sensors and thermal cameras are also being used to scan for hotspots and map changes in surface temperature. The technological tools being brought to bear on McDermitt's current awakening are among the most advanced in volcanology. Yet for all their sophistication, they can only provide snapshots of a dynamic shifting system. Volcanic behavior is notoriously difficult to predict, especially in regions that have lain dormant for millions of years. Still, every new tremor, every shift in ground elevation, every whiff of gas adds to the mosaic that scientists are piecing together. Behind the scenes, geological teams are running complex models based on fluid dynamics, magma chamber behavior, and crustal stress patterns. They are simulating a variety of scenarios, from slow subsurface cooling to full-scale eruptive reactivation. Each scenario is weighed not only for its likelihood, but for its potential consequences. Even in the best-case outcomes, the very fact that McDermitt is exhibiting such signs suggests a system far from equilibrium. Some scientists speculate that the activity could be linked to broader tectonic forces at work in the region. The Pacific Northwest is a complex intersection of fault lines, volcanic arcs, and shifting plates. It's possible that the recent seismic activity in other parts of the West, such as the ongoing tremors in Southern California or the subtle reactivation signs in Yellowstone, may be part of a larger regional stress readjustment. McDermitt's movements could thus represent a response to these larger geodynamic shifts, a symptom of a broader process unfolding in slow but relentless fashion. One of the more sobering realizations in the scientific community is that many of North America's largest volcanic features are poorly understood. Unlike the Pacific Ring of Fire, where frequent eruptions offer abundant data, the interior of the continent houses supervolcanoes whose quietude spans human history. When they stir, it often happens slowly and cryptically. This makes it all the more vital to heed the signs coming from McDermitt, even if they seem ambiguous at first glance. The ongoing efforts to understand the current activity are more than just an academic exercise. They are a race against time to grasp what nature may be signaling before it becomes undeniable. It is a delicate balance between scientific caution and public awareness, between early warnings and premature alarm. For now, authorities have not issued any evacuation orders or public alerts, but behind the scenes, the mood among geologists is one of intense focus, even anxiety. They know how fast things can change in volcanic systems. As more data comes in, the story of McDermitt's awakening continues to evolve. It may be a false alarm, a burp in the deep earth that fizzles out harmlessly, or it may be the early stages of something far more significant. Either way, what's happening beneath the caldera is real, measurable, and impossible to ignore. Scientists are watching every signal, recalibrating their models, and preparing for contingencies. One of the key challenges now is the need for more precise mapping of the underground magma system. Using magnetotellurics and seismic tomography, teams are trying to create a 3D image of the magma pathways beneath McDermitt. Such data could reveal whether magma is pooling near the surface or still confined to deeper chambers. If shallow magma bodies are found, the risk of an eruption, however minor, would rise considerably. That would change the calculus for response planning, risk communication, and even the future of resource development in the region. While the initial signs of unrest at the McDermitt Caldera have already sent waves of unease through the scientific community, a deeper analysis of the unfolding situation reveals just how multifaceted the risks and the implications really are. Far from being limited to surface-level observations or minor geological curiosities, the strange movements at McDermitt hint at an interconnected web of underground processes that challenge long-held assumptions about ancient volcanic fields. The situation now demands a holistic understanding of not only local conditions, but also regional and even global geological dynamics. One of the most pressing angles of investigation revolves around the thermodynamic profile of the McDermitt system. Temperature gradients in the subsurface, typically monitored through geothermal wells and magnetotelluric surveys, are beginning to show anomalies that could signify movement of heat sources closer to the crust. Such gradients are vital in deciphering whether the magma is actively rising or simply shifting laterally. Recent data from thermal mapping missions indicate that heat flow in specific areas of the caldera has increased significantly in a short time span, particularly around structurally weak zones such as ring faults and ancient collapse scars. These zones, long ago carved by the caldera's explosive birth, now act as potential pathways for pressurized magma and gas. The caldera's structural complexity is one of its most dangerous and least understood characteristics. Unlike a simple stratovolcano with a single vent, McDermitt is a caldera complex, an intricate lattice of collapsed chambers, intrusions, faults, and hydrothermal channels. Within this chaotic interior, it is exceedingly difficult to determine exactly where magma may surface if an eruption were to occur. Historical analogs from other caldera systems, such as Long Valley in California or Campi Flegrei in Italy, demonstrate that such features often erupt from unexpected locations along the margins or through small satellite vents far from the central depression. At McDermitt, the same unpredictability looms large. Adding further urgency to the investigation is the interaction between tectonic stress fields and magmatic pressure. The McDermitt region straddles the northern edge of the Basin and Range Province, a vast zone of crustal extension characterized by block faulting and widespread seismicity. This means the Earth's crust in the area is being stretched and thinned over time, creating zones of weakness where magma can more easily rise. As regional stress accumulates due to broader plate movements, these fractures may become the critical junctions where magmatic intrusions exploit pre-existing weaknesses in the lithosphere. It's this interplay between magma and tectonics that renders the current movements at McDermitt particularly volatile. Scientists are also examining how deep mantle processes might be influencing the caldera's current state. The Yellowstone hotspot track, which McDermitt lies at the westernmost tip of, was created by the North American plate moving over a fixed mantle plume. Though the active upwelling has long since migrated eastward toward present-day Yellowstone, residual thermal anomalies could still persist beneath McDermitt. These anomalies can remain geothermally influential for millions of years, quietly contributing to magmatic differentiation and fluid mobilization beneath the crust. If lingering mantle heat is rekindling long-cooled magma bodies, it could explain the sudden signs of unrest. Another lesser-known but potentially pivotal component in the equation is the presence of extensive clay-rich hydrothermal alteration zones within the caldera. These zones, formed when volcanic fluids reacted with the surrounding rock over geologic timescales, now contain high concentrations of lithium-bearing clays like hectorite and smectite. While economically valuable, these alteration zones also have unique thermal and mechanical properties. They can act as semi-permeable membranes, trapping gases and fluids beneath the surface until pressures reach critical thresholds. If overpressured fluids suddenly breach these clay seals, the resulting hydrothermal explosions could act as precursors to magmatic eruptions, or as eruptions themselves, in a phreatic form. This dynamic has been observed in other volcanic regions, where hydrothermal systems transitioned violently into eruptive phases. For instance, the 2014 eruption at Japan's Mount Ontake was triggered not by fresh magma, but by a sudden release of superheated groundwater. McDermitt, with its vast hydrothermal legacy, may be vulnerable to similar behavior. Satellite thermal sensors have already begun to pick up subtle changes in surface temperature in areas where fumaroles had previously been dormant. Some researchers are now conducting soil gas surveys to detect radon emissions, another telltale sign of deep magmatic intrusion and fluid migration. Beneath all these observations lies an unsettling truth. The McDermitt Caldera is being recontextualized in real time. What was once considered an inactive or extinct feature is proving to be more dynamically active than previously imagined. This has sparked debates within the volcanology community about how to classify such calderas. The traditional taxonomy of active, dormant, and extinct may be too simplistic to encompass the complexities of long quiescent caldera systems that can reawaken under the right conditions. The scientific community may be forced to adopt a more nuanced spectrum of volcanic activity, one that acknowledges that even millions of years of silence do not equate to permanent dormancy. The sudden shift in perception has triggered a race to update the region's hazard assessments. Local and state agencies, previously focused on wildfire risk and water resource management, now find themselves grappling with a new category of potential natural disaster. Emergency response frameworks are being reviewed, evacuation routes reanalyzed, and communication strategies retooled. For a region unaccustomed to the threat of volcanic eruption, preparedness is both a technical and psychological challenge. Rural populations may lack the awareness or training to respond effectively should conditions escalate, and even the logistics of monitoring such a vast and remote area are proving daunting. On the scientific front, the anomaly at McDermitt is becoming a case study for multidisciplinary cooperation. Geophysicists, geochemists, structural geologists, and volcanologists are all converging on the site, each bringing unique methodologies to unravel the puzzle. Satellite data is being cross-referenced with ground-based observations, while AI-driven pattern recognition algorithms are being deployed to process the enormous influx of seismic data. This convergence of expertise and technology is yielding unprecedented insights, not just into McDermitt, but into caldera dynamics more broadly. There's also growing interest in how changes at McDermitt might influence environmental systems, especially given its proximity to sensitive ecosystems. Volcanic activity, even without eruption, can lead to the release of heavy metals and acidic compounds into nearby watersheds. If hydrothermal activity begins leaching these substances into surface water, it could threaten fish populations, contaminate drinking water, and degrade soil health. Already, preliminary tests show a rise in certain elements like arsenic and boron in some of the shallow aquifers near the caldera rim. These findings are early and inconclusive, but they raise red flags that environmental monitoring agencies are now taking seriously. From a climatological perspective, there's interest in what a reawakening at McDermitt could mean on a broader atmospheric scale. While only the most extreme eruptions have climate-altering impacts, such as those of Tambora or Pinatubo, even a moderate eruption can inject large volumes of sulfur aerosols into the stratosphere, temporarily cooling global temperatures. Though speculative, researchers are now modeling potential emission outputs under various eruption scenarios. These models help inform international bodies that track volcanic contributions to atmospheric chemistry, particularly in the context of anthropogenic climate change. As researchers delve deeper into McDermitt's structure, One of the more surprising findings has been the presence of remnant magma pockets left behind from earlier, smaller eruptions after the initial caldera forming event. These pockets, known as cryptodomes, are difficult to detect with conventional instruments, but have been revealed through deep penetrating seismic imaging. Cryptodomes can behave unpredictably. If reheated or pressurized by newer intrusions, they can rupture explosively, similar to what occurred at Mount St. Helens in 1980. Their identification within McDermitt adds yet another layer of complexity to the unfolding narrative. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on the strange McDermitt Caldera movements? Could eruption risks rise? We want to hear from you. Thank you for watching and see you next time.